Mizoram University. So, without giving a more elaborate description, because his list is long, so to keep it short, I would request, sir, I'm very happy to have you here online. If we could have it physically, it would have been better, sir. So, thank you very much for consenting to be part of this. Both our IT department and electronics department is jointly conducting it, this particular program. Uh, over to sir.
Okay, thank you very much, Dr. Swanivar Mazumdar, the head departments of IT, Tripura University. And thank you very much for giving me opportunity to share some of my thoughts and idea in this field. Uh, as you have also already mentioned that this topic, the participants are coming from the IT background as well as from the electronics background. But maybe for the IT, it might be little uh, out of the tracks for this topic which I have chosen. But anyway, I will not go much on some certain things which so that the people should not have that much the boring. But I'll try to make the topic a little generalized way so that the people can have a little interest on the thing. And then at first, I would like to thanks again Dr. Swanivar because I have requested him to please allow some of my MTech and BTech students also to participate in this your FDP, where they are also having this antenna and the microwave subjects. But he kindly allowed us. Thank you very much, Dr. Swanivar, again.
Thank you, sir.
Uh, Thank you. Now, coming to my today's talks. Today, I will be delivering a talks on uh, this. Uh, my talks will be on the effects of the ground plane on microstrip antenna performance. Is my voice is audible? No?
Yes, sir.
Okay, okay. Uh, here, what we are going to do is that we have a one kind of the antenna. Antenna is nothing but is I'll just try to start from the little basic. Please don't mind those who have already in this area. The antenna is nothing but any device which can radiate or which can receive electromagnetic wave. Either it can be as a transmitter or it can be received. Okay, so here, but in general, the antennas definitions are like this. And again, in antennas, we are having the different kinds of the antennas. Like just like I'll just like to take one kind of the antenna, which the many of us are having the Dix antenna at our home. This is a one parabolic Dix antenna is there. Okay, where the reflectors is there and the feed is there. So there is one parabolic reflector antenna, and in the BSNL office also, oh sorry, in the telecom offices where the transmission and the reception takes place also, many antennas are there. And even nowadays many in the our localities also there are different this service provider antennas has been put up in the localities. Okay, but here I will be concentrating only to one particular antenna, that is we call as a microstrip antenna. Where is the microstrip antenna is that I just like to highlight that the microstrip antenna is a very planar kind of the antennas which has many advantages as well as some certain disadvantages is there. But where can we see any microstrip antenna is that in every cell phone which we are having over there is a one antenna is there, that is we call as a PIFA antenna is there in our our cell phone, that is our mobile. This is also a kind of the microstrip antenna. Okay, so like in the antennas, we need to be very have to be very much portable, as well as it should be planar structure. Like example, if we carry a DICS kind of the antenna in the cell phone tower, then it will be very much inconvenient to us. So in that case, this kind of the antenna is being introduced. That is a microstrip antenna, microstrip antenna. So here, even like example, nowadays we are having the various wearable antennas are there. The antenna can be a part of our the buckles, or maybe with the with the buckles of our belt, or maybe with the buttons of the shirt, or maybe it can be on the cap which we use for various application, GPRS trackings and all those things, like to find the location of the soldiers and all those things. But in such kind of the where it is a wearable antenna, where to carrying a very big antenna of the DICS kind of the things which we see in our DICS in the home for our televisions, those are not very suitable. So in that case, different kinds of the concepts of the antennas are required. So here it has been coming with this kind of the microstrip antenna. So let us just see what is this microstrip antenna first. Then after that, I will come down to the topics which we want to discuss. I want to discuss little bit, and these topics which we've been covering is something. First, I will just be going with the little on the of the basics. Then after that, it will go to the some on the research area, and I will be presenting some of our finding also. So I hope this will be quite maybe useful for the some people who are working on the this area also. So the outlines of my presentations, I will just try to cover the introductions of the microstrip antenna for the sake of the clearing the concepts of the what is an microstrip antenna. Then after that, I will be concentrating on there is a one plane we call as a ground plane. Okay, so on the ground planes, what effects of the different ground size of the ground plane on microstrip antenna will be discussed. Then after that, effects of the ground plane in the broadband microstrip antenna designs will be discussed, and then again the effects of the ground plane in compact patch antennas will be discussed, and then effects of the ground plane in the polarization purity. So this parts I will be discussing mainly this areas. The main four focus will be there in my discussion, and then conclusion and the references. So now let's see what is this microstrip antenna. Microstrip antennas. Antennas is a kind of the radiating pads, or we also say as a microstrip or the pads. And what happened is that in this is a we all know the PCB. PCB is there. In the one side, both sides is the metallic copper films are coated. Okay, the person who don't know this microstrip antenna, also we can just imagine that we have a PCB is there. That because as all will be from the engineering background, either from the IT or maybe from the electronics also, as we all know the PCB, where in the both side there is the copper films are there. So what is in the one side? So but in between these two copper films, it is separated by one material that is we call as a dielectric substrate. So depending on the kind of the material, it will have the different dielectric constraints will be there, and we use the different kinds of the material for the different applications also. So I think in the second point, the pads is generally made of conducting materials such as the copper or the gold, and it can take up any possible shape. But for it can have any shape, but for the better analysis and the prediction, normally in the books and in general we used to find define to some particular structure, like, but it is not limited to this structure. It can be of any shapes. We also have done the work on the different shapes also, but for the easier analysis, because for the mathematical derivation and all those things, one is the square and another can be square, or the rectangular is and another is a circular. It can be triangular, it can be elliptical, like that. But here, what are some certain things which we need to choose for a rectangular paths, is some certain the typical dimension, the length and all those things like that. Suppose if the length is which we are choosing should be between the 0.333 lambda, and it should be less than the zero point 0.5 lambda, means lambda by 2. This is nothing but the zero point 0.5 lambda is nothing but the lambda by 2. Lambda by 2 is a very much popular antenna. There is a your Yagi-Uda antenna and all those things, which maybe many of our friends may not have seen it, but during our childhood time, when all these digital TVs before starting, and your this cable TVs before that one, when there was only Doordarshan was there, there was a big antenna with the metallic aluminum structure, which is having around, one will be a round little folded one, another other three or four elements will be straight one pipe, aluminum pipe type. That those is we where is we call as the Yagi-Uda antennas. Okay, over there. So the length of the here the length, that is also called as a lambda by 2 Yagi-Uda antennas. Okay, but here lambda by lambda, here the length of the rectangular path should be between the 0.5 lambda to the 0.33 lambda, like that. And where the lambda is nothing but the lambda no is the free space wavelength. Okay, so and another is that the thickness of the material, that is a copper, should be very much less than the wavelength. Okay, is the thickness of the paste, the copper film. Like example, in the PCB, that copper film is grown on the substrate, or that is the thickness should be very much less than the wavelength. So it is in terms of the micrometers. Okay, so that's why we call as the microstrip antenna. Okay, microstrip antenna is the thickness is very less in terms of the micrometer level, so it is, that's why we call as the microstrip antenna. And the height of the substrate means the separation between the pads and the so separation between the two conducting layer. One will be called as the patch antenna or the antenna, or microstrip antenna, or on the other will be going to be called as the ground plane. Okay, so the separations has to be approximately the ranging of that ice is being given here. Ice is being given here. It should be between this some certain range, and the dielectric constant for typical should be around 2.2 to 12. Okay, but this is a just typical range. I myself also even work with the ear dielectric. We have published some of the papers with the ear dielectric also, and this is just a typical range. We can change it. Okay, so up to the some certain other range also, other dielectric constant, high K dielectrics and all those things can be also used for the different application from time to time. Okay, so this is an antenna. So this is a substrate. This is a substrate, and the downside is also the conducting layer of the thin films of the copper, and upper side is also a copper radiating pads. This is we call as a radiating pads or the microstrip antenna. And in between this two conducting layer, upside conducting layer, and this is the downside conducting layer, is separated by a dielectric constant. The shape of the pads can be anything. It can be circular, it can be rectangular, it can be square, it can be triangular, or it can be E shape, and it can be F shape, it can be L shape. Different shapes are there. Okay, so the side view again, we can just see this is your coaxial fit. Okay, it can be of the different fit, but here I have just given an example for the coaxial fit. And the downside, the little thickness is there in the here. This is a copper is there, and the upside also is copper is there. So these two are separated by the dielectric constant, and this is the height of the antennas. Okay, normally this is a very low, so it depends on the 1.2 or 1.3 for like the different height there. According to that one, it will have the various applications. And even like example, what also we do is that if suppose if it is the ear dielectric, then the thickness can be varied. It's up to the our choice, because other specific uh, antenna which is having the other either the FR4 or the epsilon, which is FR4 or maybe RTEIT or any substrate, if we have to procure from the market, then there are only few specific thickness are there. So according to that one, we have to design the antenna. But if I choose ear dielectric antenna, then the this height can be changed as per as the my requirement, as well as the depending on the optimized value. So now let's see what in brief I have just discussed about the microstrip antenna. Now I'll just see about some certain advantages of the microstrip antenna, as well as some certain disadvantages. I'm not going to do much on the exactly the analysis. I will just come directly with my topics, what I just be going to be discussed. But what are the advantages of having this antenna? Is it is a very low weight, and a very as in our mobile phone, it is a very low weight and a low cost. It can be go for the means large production, okay, low cost and low volume, and low fabrication cost. The antenna can be easily mounted on missiles, rockets, or the satellites without any major alterations. Okay, it is not going to hamper. It can be wrapped around the body itself, of the your missiles or the rockets. So it is not a big issue. It is not going to without any major alteration. This is what is the meaning. Then after that, we have the yeah, it can be dual frequency antenna, can also be easily made. And yeah, it actually this is a general dual frequency that we even work with the we have designed this, some antennas which can work at the not only dual, it can work in a triple, and it can be work at the quad, it can be work in the penta, it can be work with the hexa. Up to hexa we have designed, and but even beyond that also the people, some there are some reports are already there. Okay, so it can support both. We have the polarization. It can support both linear as well as the circular polarization. The circular antenna can have this one linear polarization as well as the circular polarization. So in the when we I was discussing about the compact antennas, where there are some circular polarized antennas also been discussed. But what are the disadvantages of this antenna? One is this narrow bandwidth is there. Another is the low power handling capacity, and its efficiencies are also little low, and it is having the low gain. But there are many various reports are already there. Even it can have the very large bandwidth can be obtained. Even it can obtain the ultra wide band also. That I think in even my in presentation we have also some certain antennas which work in the ultra wide band also. Okay, and even it can handle this power handling capacity. It cannot be handled very large power as like of the parabolic and all those things like that. So there is some certain limitation. But there are the reports are there where it can have some certain power handling capacity can be increased, and if efficiency is also. But now normally we can obtain efficiency up to the 80-90 can be easily obtained, and the low gain. This is typically the gain of the microstrip antenna is coming to be around one to two, 1 to 3 like that. But now many reports has already been already there. Even we also have already done some work. Even the gain can be increased up to quite a large values. Okay, so this kind of the disadvantages are it is in the this conventional microstrip antenna. But we have done lots of many engineering on the antenna, and then after that we can have changed lots of things on this. We can overcome the many of the drawbacks. Okay. So now let's come to the what is the effect of the ground plane. Actually, why I am be discussing the effect of the different kinds of ground plane is that we have an antenna is there. Suppose this antenna, the size of the overall antenna is going to be also affected by a ground plane. Maybe suppose let us say that if the antenna size is the size of the this nail of a thumb, but if it is ground plane is size of the A4 paper, then the size of the antenna will be considered as the overall size of the antenna will be that size of the A4 paper. It will not be just size of the thumbnail size. So what our study is that how much we can make the smaller the ground plane and what kind of the shape will be suitable for the what kind of the pets. This some little study was done by us. So in that regard, so because that is the ground plane size is going to be have the overall effects of the antenna. Suppose as we know that inside the my our cell phone, my mobile phone, there is a microstrip antennas are present there, but the pipa antenna is present there. Microstrip pipa antenna is present there, P structure, P shape. But if let us say that the size is a very small size, so it can be fit easily in our mobile phone, but if let us say that the size of the ground plane is the size of the A4 paper, then it will not be able to fit. Even if your antenna is small, if your ground plane size is very large, then we will not be able to fit that antenna in the this one. So our studies was aimed to so that how much we can reduce the ground plane. There are specific the typical some standards are there, but our aim was to study that what kind of the structure is suitable for what kind of the antenna. That was the things. So in that regard, what we did was we have done was the mainly with the we select the some certain standard size. One is the square shape pads. What the study what we have done was the square shape pads with the here the square shape pads antenna with the different size of the square or the circular shape ground planes are studied. Then again another is a circular shape pads we have taken it antenna, and then with a different size of the square or the circular shapes of the ground planes were studied. When the same size of the square pads with the square ground, when the pads and when the ground planes are of the same size, then what will happen? Radiation on the pad side and the radiation on the back side will be equal, exactly equal, and it will be just look like as a dipole type. Okay, the one pole will be in the this side, another pole will be in the this side. So that we have observed it, but what we have done was that for the square pads with the circular ground plane of the same equivalent area, but in that case we found is that the back lobe is must the actually which has to radiate in the pad side is not radiating, and when it is radiating mainly on the back side. So that we have found a large this one back lobe in the case of the square patch with the circular ground plane. So that which was the observed, I think we can see in some certain okay, that result also we will show. And when the same size of the pads with the circular shape of the ground planes give the equal amount of the front and back lobe ratio, but the circular pads with the circular shape pads, then it will give equal amount of power in the front as well as in the back. Back means that below the ground plane also. Actually, we don't want that radiation should be takes place below the ground plane. Okay, so we don't want that any radiation should be takes place on the this back side. We want sorry, we want that antenna should radiate it on the this side, in the patch side, but if the size is become smaller and the smaller, it will start radiating on the back side also. Okay, so that was happened. So we try to see how much we can reduce it, and if it is the same shape is there, then it will be radiating equally in both sides. But what we have observed is, I think, is mentioned here. When the circular patch with the square ground plane of the same equivalent area, then the front lobe is coming to be around this large gain, and the back lobe is coming to be much smaller. So so the what is our suggestion is that the circular, if there is any many of us also work with the circular patch, but in that case we should select a square shaped ground plane, so that it will have the less effect on the this back lobe. Back lobe will size will be much smaller in this regard. So at least we have to have that kind of the this one, and then it will be good. Okay, we can just show a small some finding like here. What we did was that in this case the square patch with the circular square ground is, we have studied another square patch with the circular ground, and another case is the circular patch with the square ground, and the circular patch with the circular ground. So the patch is in the upside, substrate ground plane is on the downside, and we are doing the prop feeding, coaxial prop feeding. Then what we found is that if the size of the patch and the size of the ground planes are same, in the case of the circular patch with the circular ground plane, it will be radiating equally in the ground plane side as well as in the back and the patch side. Similarly, if it is for the square also, it will radiate equally in the both in the front as well as in the back lobe. But what happened is that this case, the rectangular square or the rectangular patch with the circular ground is the worst case. It's not good to have such ground plane. Okay, so what we observed was that if it is the circular place, if we are working, and we should always use the square ground plane, so that we can make the antenna as small as ground plane up to a considerable range of the, it can make it smaller. The study was conducted for the square patch with the square ground plane. What is happening when the ground plane is reducing, the size is, when the size of the ground plane keep on reducing, what happened to the pads and all those things like that. That is been study has been done, and similarly we have done it for the square pads with the circular ground, and then we have checked. So here is that if the ground square pads with the square, it will be radiating equally in the, this is we call as the front lobe, and this is the main the front side, and this is the back side are equally radiating. So this is not desirable at that application, but when this is the case when the square this is the case when the square patch with the circular ground plane of equivalent area, because the area of the square is nothing but you're laying into breadth or the L square, and the area of this circle is that your pi r square, like that. So we have measured equivalent area. Then the back lobe found to be more than the front lobe, so this is not desirable. But this is the case when the circular patch with the circular ground plane, if it is same size, then it is equally radiating. But here what we observe is that when the circular patch with the square ground plane of the equivalent area, the front reverse has been happening, reverse of this one. In this side, back lobe is increasing when the square ground plane is used for the circular patch. But here is that circular patch with the square ground plane. So the radiations are been reversing. So this is one of the achievements. I think this study it was found, and it was quite good, and we also got lots of citation with this particular studies for selecting the ground planes. Okay, this is all paper. So those are findings which I have been just discussing. Was it is in that details, we can just skip. Now is that that was a small studies, but small but a very informative studies was done. effects. And then the next is about our ground plane on the broadband microstrip antennas. So here the effects of the ground plane in the broadband microstrip antenna. What we are going to do is that there we can do many things on the paths itself, also by cutting something, or by putting some kind of the holes on the paths, or cutting some part of the path. But my work here in this presentation, I have just selected only those with the effects on the ground plane. That is, we in general we call as a DGS, defected ground plane. DGS, defected ground plane surface. Okay, no, okay. So the here the mainly in the ground plane the effects we have in studies. So what we can see here is that the with the change in the shapes of the ground plane, we can achieve. Suppose let us say that one antenna is there where bandwidth is around 39.56%, with the gain of the around 7.82 and the 8.78 as a peak gain. And then if suppose if we have provided some different slots on the ground plane proposed antenna, and then from 39.562 it can reach go up to the 67.49% can be obtained in one of the our study. Like example, here it is shown here. Like this is the shape of the paths. Here is we have selected a one E paths. This is one of the broadband antenna, and we also have this published this paper on the paths, E paths. But here in this study, what is we have done is that in the this is the paths, the E shaped paths, and then after that the ground plane which we have defined this kind of the slots, or this kind of the slots, this kind of the slots. We have tried a lot with the different kinds of the path structure. Then we did a study what is affecting. Basically, if we cut something on the ground plane, the back lobe size is going to be increases. But the meantime, also we try to maintain the back lobe size also. So some certain studies where I don't know, result may not be interested for some people. What our intention is that if we put this ground plane will be replaced the regular ground plane. Regular means where there is no any cuts are there. It's been replaced by this kind of the shapes. Okay, and this is A is being considered as a conventional, and the B, C, D, E are the different shapes of the ground plane which we have introduced, and these values are optimized values. Okay, it is not that we have just been figuring after doing the lots of optimizations, then through the software. Then after that we found that this parameter, like example 24 millimeters, and the gap is a 4 millimeter, like this kind of some certain gaps, and this kind of the parameters we obtain it after the proper optimizing the things. After optimizing means we have to see whether the proper return loss is maintaining or not, like that, and as well as whether front to back ratios are properly maintained or not, like that kind of the things. So here the structure which the proposed was 39.56% the bandwidth, the frequency ranging is from 4.842 gigahertz to 7.23 gigahertz range. In the radiation pattern at the around to the center frequency means at the 6 gigahertz has been given here, like that. When the ground planes are introduced, then we found that there is when the ground planes has been replaced by this kind of the structure, then there is the increase in the bandwidth has been obtained, and the radiation pattern and the gains are observed. So if that kind of the structure is introduced from the earlier, we said that it is the 39.56 with this kind of the structure, we have obtained a 46.5% bandwidth. Then after that, with this kind of the structures, which after optimizing, then we found the bandwidth of the around the 46.5%. Then again, this kind of the structures which we have introduced, then we got around 47% 0.41%. The bandwidth has been increasing, but the main time we also compromise some certain things with the gain. As we know that something is cut on the back side, the back lobe is going to be increased. The back lobe, when the back lobe is increasing, the gains are been reducing, but the 6.6 or 6.4, the gain in a microstrip antenna is considered as a very good gains. Okay, we can consider it's a good gain. And even this kind of the structure when we introduce, then we obtain, this is the, as far as the different, we have studied a different kind of the shape, but out of that we have found those four structures are suitable for that kind of the E-pads, E-shape pads. If it is some other shape of the pads, it can be F-shape pads or something like that. Then whatever which we are proposing here may not be applicable. In that case, it may give the good gain in some particular structure of the ground plane. So here additional resonance has been introduced. So because of the additional resonance, all are between below the minus 10 dB in the return loss. So we are getting a large bandwidth of around 57%, which we obtained with the this shape of the cuts on the ground planes. So this was the best designs so far in this that particular paper of the particular studies for the particular shape. So this was one of the papers. Okay. Uh, then similarly, what we have done it is some studies was conducted with the kind of the earlier it was the E shape. Now we have study was done with the double L shape. Double L shape was also done it. Double L shape was also done here. Then in that case we have try the ground plane. We introduced like this, and then okay, and we introduced like here is a 2 and the 4 we have introduced. Then this kind of the structures which we have introduced like that. And even this kind, earlier it was a triangle shape, a proper triangle shape, but now it become the angle become the more than 90-degree. Is kind of the structures we have tried, and then we did the analysis for this one. Then what we can see is that the result, I'll just come down to the result, is that in the conventional one it was 28.24. 28.24% is the bandwidth. Now with the different shapes around, it has moved down to the move up to the 33.34, 32.24, and 33.48, and the best one which we have obtained is the 34.3% with the case number 4. In this case, this kind of the structure, this case is found the largest bandwidth. But in the earlier case, it was giving, because the shape of the patch was the E shape, so it was giving the best result with the 2 slots. But now at this particular shape of the patch structure, the double L shape, where we found that this kind of the structure give the best result to have the larger bandwidth. So this then again we have done some study on the W shape also. W shapes also we have done it for the W shape also. We have done. In that case also we try with the different types of the ground planes. The ground plane slots which has been introduced like this, like this. All we have tried. Okay. Then we try with the different 4 shapes of the ground plane. Now let us see which is in this case what is the best which we have obtained was when it was this one regular shape, then it was 42.37%. Then after having the different ground plane, it will go up to the 50.52, 49.65, 48.49, 52.06%, like this. The bandwidth is been increasing. But what happened is that from here also we can see that the gain has been reducing. Earlier, when there is no cut, it was around 10.269, but when the cuts are introduced on the defected ground, the gains are slightly reduced. These two which we are mentioning here is one is the peak and another is the average gain. Peak is the like example out of this, which is the most highest, that is the peak. Then the average is that within our bandwidth from here to here, what is the average gain, like that we have find out. Okay, that is the average gain. Like 5.38 to the this 9.81, like then from 5.83 to the 9. What is the average gain of the from here to here, the bandwidth? Okay, and the peak is this one that we have found. So the peak and the average gain, these are quite good, but it is slightly lesser than the conventional ground structure. And then we have done some certain studies again with the defected ground plane, with the ultra wideband, with the stable gains and all things like that. This is applications of the defected ground structure on a stable gain with the ultra wideband. What we did was that we tried to introduce this kind of the ring slots on the ground plane. Okay, ground plane was introduced, and we found that this analysis was done, and the ground plane the gain was increasing quite a large. So those results and all those things are obtained here. This is defected ground plane in a different way of approaching. So over here, and the gain are also quite stable. There is no large variations is observed. Like in the previous gain, the gain was going from around 10 point, and it was lowering to the some certain. But this is quite stable. It is variations are between around 4 to 5.5, something like that. Okay, so it is quite stable. Gains also we obtain, and then so here we obtain around 47% this impedance bandwidth with the proposed structure of the defected ground structure surface DGS. This was also the one of the paper. Then the here what happened is that another paper which is been here, the mention is that over here that we have the DGS defected ground surface structure with the integrated ear loaded for the wideband microstrip in the X band and the KU band. As we know, the X band is from around 8 to 12, and then KU is from the 12 to 18 gigahertz. So this antenna can work in both the X and the KU bands. And let us just see how this looks like. This is one of the IEEE papers. This DGS ear loaded wideband microstrip structure for the X and the KU band. So here this is the normal path. Oh, sorry. This is this kind of the slots we have introduced here with the kind of the little sorting post also we have introduced. Sorting post, I think there may be some sorting post also we have introduced, and it can be work in the its bandwidth has been improving a lot, and then the frequency range which is covering is both your X band as well as the full X band and some part of the KU band, that is from 12 to 14 gigahertz. So this is the structure of the antenna. This is the pads, and then this is the back side of the. There is a ground plane side. The cut is already made over there. So this is a probe which we fit. The coaxial probe is fitted over here. Okay, I just want to show. So here what is we are mentioning over here is that ear loaded means ear loaded. We have introduced a small gap of ear in between the dielectric. This is the pads. This is the first yellowish color is the pads. Then the gray color is the dielectric substrate, and then between the dielectric and the substrate, we introduce a ear gap. Air gap is introduced in between the substrate and the this ground plane. So because of the this one also we are getting a very large bandwidth. That's why it can work in both the X band and as well as in the C band. So it is it is working around to the 58.7% percent. It is working. This is between around the around 8.3 to around 15.2 gigahertz. The all antenna is working within this any frequency within this range. Another application of the defective ground structure for augmenting high gain, we are trying to introduce. Earlier it was we also say that the low gain is also the one of the disadvantage, but due to the unconventional way of approaching, and we can also overcome those low gain. So this is, let's just see how this structure is look like. This is also the one of the paper electromagnetics. So here this kind of the slots has been introduced on the ground plane. Then we obtain quite a good gain, as well as we obtain a quite good gain. The gain is around the 9.1 to 9.4 and around 58% of the impedance bandwidth, covering the whole of the KU band. KU band, as is we know that from 8 to around 12 gigahertz, 12 to 14 gigahertz. So the large bandwidth which we can obtain it. Okay, this is the was proposed in the this electromagnetic journal. Sorry, it is published in the electromagnetic journal. So with the one of our researchers. So this kind of the is the ground plane. This is the we just see the electric this one the electric field magnitude, so which we can just show it from the here. So it is covering quite a large range from around 11 point some 5 to the. It is covering up to the quite a large frequency from the 11 point something to the. So whole of the KU bands is covering with the simulated and the measured results. So see, these are the different radiation pattern. We check it at the different frequency for whether we just want to check whether it's stable or not, like that. So just to show that it is not that if there is a good gains, radiation patterns are always good. So we just check it with the different gains. So this is a very simple structure. Only thing is that in the ground plane we have introduced the 4 hexagonal. This ice represent is for the hexagonal. We have here hexagonal shapes of the slots has been cut on the ground plane, and we obtain a high gain with the. We consider the 9.1 and 9.4 are the high gain in the case of the this microstrip antenna. So this is mainly about our broadband. Now let's come to the what is the effects of the ground plane in the compact patch antennas. How can we compact in the sense that, like example, in the case of the antenna, this, as we know that when the frequency is increasing, the size of the patch is been reducing. Similarly, when the frequency is smaller, then the size of the patch is increasing. Is inversely proportional. The size and the frequencies are inversely proportional. So what we are doing is that a structure is there which is supposed to work at the higher frequency, but with the introduction of the some cuts and some slots on the ground, we are going to make them to operate at the lower frequency. So that will have a impact on the reducing the so like this the size. Otherwise what will happen if an antenna is supposed to work at the lower frequency, the size of the antenna has to be bigger and the bigger. But what we are doing is that the size is antenna, let us say this is working at the, let us say, the 5 gigahertz, but the with the some certain cuts on this antenna ground plane or maybe on the patch itself, it is going to work at the from 5 to 2, like that. But suppose if it is a conventional 2 gigahertz antenna, then the size will be like this. So the 5 which was work at the conventional one, after introducing some cuts and slot, it will be able to work at the 2 gigahertz. So it is just nothing but overall it is a compactness of the paths. So here we have also proposed some certain structures. In the this will be mainly on the compact circularly polarized antenna. This kind of the structure is the path shape, is the shape of the path. This is circularly polarized. We have the three kinds of the polarization: circular polarization, linear polarization, and the elliptical polarization. This is a circularly polarized antenna. So here we introduce some kind of the defects on this ground. Then its operating frequencies has been shifting. So and it is circularly polarized because the axial ratios of the major axis to the minor axis is, if it is below the 3 dB, then we call as a, we can consider this is a circularly polarized antenna. So here the percentage of the frequency reductions we can obtain, it is about around 21.95 reductions of the frequency can be done it with the introduction of the this kind of the ground structures. When we compare a different case, then another shapes also we have tried. What we did was that in the patch itself also we have done it. Then after that in the ground plane also, this ground plane also, this kind of the cuts are there on the and on the patch also, in the antenna patch also itself also we have cut it like this. Then after that we can obtain a, and then this one around the reduction of around 42.5% reductions of the frequency takes place. 42.5 reductions of the percentage of the reductions takes place with the this kind of the structure. This is circularly polarized, so the axial ratios is below the 3 dB. 3 dB is here, so it is below 3 dB, so it can be called as a circular this one. Around 42.45 reductions can be obtained. This is the little old paper, but this was designed for the Wi-Fi kind of the antennas. This kind of the shapes is been proposed. This kind of the shape has been proposed. Then after that we try to this one cut the, like example we can see here the we can, this is the shape, bow tie shape of the paths. Then after that we introduce this kind of the this slope or this slots at the 45-degree bending slots have been introduced in all the 4 directions like this. Then we can obtain this one with this kind of the path, so we can obtain this one around 71% reductions can be takes place. This is one of the good achievement. We can reduce around 71% of the but the only thing is that here the gains and all the things are also been little affected, but still it is a it is acceptable. It is operating at a 2.4 gigahertz. That is your Wi-Fi frequencies and everything like that. So we try with the all different here also. We study the different kind of the slots and the slots and slits. L this kind of the slots also, this kind of the slits also, but this is here uh, here we can just see the findings. The case number 3 means this kind of the structure. This kind of the structure is give the maximum reduction in the operating frequencies has been obtained with the 71.3 percentage reductions in the with the reductions of the frequencies can be takes place. This is one of the very good achievement, and the same time we did not have the much the gain, but the only thing is we know that the reference was the gain was around 5.62, but it has go down to the 2.71 because the slits has been introduced on the ground plane. But at least the 2.71 is a good gain for the Wi-Fi kind of the antennas for the indoor applications and all those things like that. It is a good and acceptable. One of the antennas also we have presented similar types. This is also the one some of our students prepare. We have the circular polarized with this kind of the cuts. We have made it on the patch itself. Then we can obtain the quite this one good reductions with around 23.7%. Here the two ground plane structure. One is the this kind of the slots. The another. I think only one. Okay, only one case is been studied. It is supposed to be two cases. Yeah, another case is here. So here, in the both cases, percentage of the reductions has been coming to around one is around 11.03, another is around 23.7. And this one of the, I think IEEE conference was published. And this is the one some ATA which was held in the Mumbai one. Similar types of the structures are there. Now let us see the effect of the ground plane in the polarization purity. Here what we are going to discuss is that as we know that the what happened is that the polarization purity where we are going to mean is that as we know in general term is that we have a one co-polarization and another is a cross polarization. Co-polarization is the polarization along the desired directions. Okay, cross pole is along the undesired direction. Signal, let us say that I want to radiate a signal in this particular directions. Okay, I want to radiate the signal in the, let us say that this is my antenna. I want to radiate in the this directions. I want to radiate it, but what happens is that it may radiate along the horizontal also. It may radiate some certain signals on the horizontal. That the difference, how much is the difference between the your this is let us say this is a co-pole, this is undesired direction is a cross pole. How much is the difference? We'll be able to we can call as a polarization purity. Here with the using the defected ground plane, we can obtain a very good polarization purities also, and we have a lots of paper in the some in the IEEE and also like that also where we have work, but here I have just selected only the work which has done only with the ground plane. We have done the polarization purity can be obtained with the, many other techniques with the cutting something, introducing the ER loaded, or it can be putting some kind of the slots or some kind of the other structures on the pads. That part I have not included. This is specifically only my work, my presentation is concerned only with the effects of the ground plane only. So I have just selected the papers which is related, which we can obtain the good polarization purity only because of the ground plane. That kind of the paper only we have selected here. So the so let us just see how the kind of the structures has been. This is one of the paper which was actually, it's a 2014 paper. So here, this is a rectangular microstrip antenna on a slot type defected ground for reduced cross polarized radiations. So what we have done is that we can just see, this is the top view of the antenna. This is the top view of the antenna. And this is a side view, and we can very clearly see that here the black one is the patch, this patch, and in the ground is a, we have discontinued, we have cut the slots on the ground, we have cut the metal on the ground like that, we have etched out this ground like this. So then after that we found that there is a very good cross pole has been suppressed. So without, while suppressing the cross pole, the effects, it is not affecting anything on the radiation pattern of the cross pole. This was the main work of this paper. This is the main work of this paper. Okay, so that's why it is defected ground structure on the slot types of the defects on ground for the reduced cross pole radiations. Okay. So we can just see some of the results. Here also the front to back ratios also, okay, this is also quite reducing, and similarly these are the different co-pole and the cross-pole pattern. Here the co-pole patterns are here, okay, and these are the cross-pole patterns are here. So here we can reduce, we can suppress the cross-pole up to quite up to 25 dB. The co and the cross-pole differences can be reduced up to the 25 dB. We can reduce it. Okay, this from here to here, co and the cross pole we can reduce up to the 25 dB. Means the signal transmitting in the desired direction is above 25 dB above your undesired directions. So that kind of the polarization purity around 25 dB is quite a good suppressions which we can obtain it with that kind of the introduction of the slots, that is which we have shown it in this particular paper. All the co-pole and the cross-pole without DGS, means DGS means defected ground structure, as well as the defected ground. So see here, what we can see is that this blue one is without DGS. Non-DGS means the regular ground plane. What happened? But with the like example here, this kind of the little purple color and other green color, these are with the DGS. Means after that the cut has been introduced, you can see suddenly it has been dropped down. So this kind of the this is the differences is been coming to be in some places, so it is coming to be around 45, but on average we can say it is beyond above 25 dB, which we can easily obtain. So the above 25 dB is a very significant result which we have obtained it. With the simply we are just introducing this kind of the cut on the ground plane. The pads is be remain as a circular rectangular pads only. The cut has been introduced. Without cut and with cut we have analysis. Okay, then after that we have already seen is the non-DGS means without cut, and DGS means after cutting the defected ground. DGS means defected ground structure. Okay. So the none and this DGS like this. Okay. Then the next one is also one of the paper. Okay, let us just see. This is related with the this study of the polarization purity of a rectangular microstrip antenna integrated with a pentagon dumbbell shaped defected ground structure. So here what we have done is instead of the regular slot, we introduce a pentagon dumbbell shape defects. We have introduced it. Okay, so we can just see what is the this kind of the dumbbell shapes are there. This was introduced like, yeah. Here is the this is a pads. Then earlier it was simply the slots. Earlier it was a slot. Now we have introduced a pentagon. This just look like as a dumbbell which we have, but it looked like it's a pentagon dumbbell shape. Okay, it's been introduced on the ground plane. Then we can obtain a very good separations. This parametric studies has been done it for the different, what will be the different when the size of the pentagons are increases, what happens and all those things like that. That part has been parametric studies was been done with the this kind of the structures, and we can the base value which we can obtain with the polarization purity improvement is around to the minus 28 dB, which we have obtained it. So here, like we can see is the isolations between the co and cross pole values. The ratios are quite good. So it is coming to be around 28, and in some other depending on the here what is the study is the defect size. Defect size here the size of the size of the S, once if it is varied, the size of the S varied, then this kind of the structures has been isolation has been obtained. So around to the size of the S is equal to around 5 mm, then we get the optimized the maximum isolations between the copole, and the CP means copole and the XP means cross poles. Okay, undesired direction and desired directions which we can obtain it for the FR substrate. Okay, so these was done it with the this kind of the in this one in will the FR4 and another is the RTEIT substrate we have tried, and this was obtained. Mm, but the only thing what we also found is that in the case of the FR4, we found the gain was stable, and the RTEIT gain was some slight changes was, but this variation is also not much, around 6.7 to around 6.6 to around the 7.45 like that. It's not a big variation. This kind of the radiation pattern, how much is the separations are being takes place without and the with cross pole. With defects, we can see that how much is the separation has been the red line is without the defects, the blue lines is the with the defects. Lots of this is the signal this radiation by the pole, and this is the cross pole. This red and the blue is this we can just see that here the red and the blue is the cross pole with and without the defects. Similarly, for the RTEIT also we have done studies with and without the defects, the cross pole separations. So, like example here with the defects, there is a very good separations of the cross pole. Cross pole means signal transmission in the undesired direction, because as we know that the transmission along the undesired directions is also affecting on the efficiency, because the transmission either is in the desired direction or is in undesired direction, we are losing the power. So in this case we found that this kind of the things has been we are able to suppress the cross pole. So the 28 for the FR4 and the around 25 for the two different substrates we have studied 25 like this. Okay. So like this, we have studied the different shapes of the ground planes. This is a crucial to have the size of the ground plane. The conclusion is that we can have the ground plane reduces with the back lobe increases, but the front lobe gain decreases in all the four cases. But we have found for the square shapes, for the circular pairs, the square shape ground should be used. It is a very good option so that our radiations can be maintained. So and as well as the smaller sizes. And then after that, the compactness of the ground, compactness of the antenna can be obtained by using the cutting on the face as well as on the ground plane, because it's basically it's affecting on the electrical length of the patches and some certain inherited properties of the narrow bandwidth can be overcome by introducing by the sloth, as we have already seen that it can go up to the ultra wide bands and the 58%, 49, 47, 57% and all things like that can be easily obtained. And another is that just in the last few example where with the effect of the ground plane we can have some kind of the polarization purity can be obtained in the ground planes, but the only I have already mentioned is here the selections have been done only from the our this one only from the which is the suppression technique, which was done only from our ground plane, not because we have done many other technique also. I did not include those techniques because my topic is related only to the ground plane effects. So with this I finish my presentations. If any queries, if I could clarify some queries, then also I will be I and if I can clarify, then I will be great. If any issues, otherwise I thanks to the coordinator, Dr. Swanibar.
Are there any questions? I can see 38 around participants. You can speak up or put in the chat box also.
Yeah, maybe I was thinking that actually, as this is not directly the electromagnetic symposium or something like that, it may be, but I did not put too much stress on the results and the design because result and designs will make quite difficult for the many participants. But I try to generalize the things without going much depth into the design concepts. I just try to represent only the results and some of the findings which may be useful for if some of our friends who are doing some work in this particular directions like that.
So
Okay.
there is one question, sir, from Saurav Kumar.
Yes, yeah, it's a good question. How these shapes you design came in mind? Yeah, it's basically actually one of the thing is that we don't have any formula like that. If I do something with that one, I can obtain it like this. There is no formula in this kind of the microstrip antenna. Till now, there are different elliptical through curve fitting them techniques has been produced, but we don't have any formulas are there. So what we have to be little thinkable in that way, so that we can think on the whether if we try this kind of at least so those only which we have presented in the paper is also where we have obtained a good result. we did not present. We also try many other structure where we cannot get the very good results. So only this kind of the concepts, the things has been come in mind only with the doing the things, after doing the things. At first, it is, yes, it is a very good question, as well as it is a whether we also thought like that if we just cut a small piece from the antenna, suddenly we may got this one like that, but sometimes it is not happening. So we have to do lots of work, and after that only the things got it. Then after that only we could properly be presented in the conferences or in journal only. So those shapes are not only the what we have studied, many other shapes also we have studied, but we could not get the good results. That's why those one. But the thing is that those shapes which we have tried, which was not success, it can be a good for some other another shape of the patch. This is always a surety. That's why it is a when we need to do lots of literature survey, so that what kind of the shapes the people have explored it like that, so that I can think of their techniques and their ideas. But the most of the things what we have proposed was the we also thought, let us try with this one, and then like with our some of the our students. Then after that, those results has been obtained. But still that is, we cannot say that that are the best results. Still, the people can explore by seeing our findings. Many more can be done it again. Then the more new structure, the new structure can be come up. Like that. Yeah, hit and trial and experience. With the, I said the literature review is very much needed in that case, because we don't have any formula in this regard.
Any other question?
But later on, we also have developed some formulas. We have already developed some certain formulas for some certain design concepts and all those things like that. But the thing is that those will be fitted only for some certain range of the frequencies. When the frequency changes, then it will not be fitted again. Suppose which I have designed today, it was ranged in mainly in the in the around to the X band and the C band. Suppose this structure will not work at the another band, L band, or maybe in the another Ka band or something like that, because the we is there is effects of the this probe, because the probe and the slots introductions is also changing with respect to the there will be inductance effect. The probe is introduced means it is introducing the some inductance effect. The slots are introduced, so it introduced the capacitance effects. So overall the impedance is been changing, because when the frequency changes, the your XC and the XL is nothing but the 2 pi FL. So frequency changes, the your XL is changing, and the frequency changes, the your XC is also changing. So the design which we design, it will not be fit in the some another band like Ka band or something like that. Okay, this is also the one of the challenges. I
So
think,
anybody else? So if there are no questions, thank you very much, sir.
okay.
I was totally out of touch for last 3 years with electronics. That is mainly the antenna microwave part. Thank you from my side, because I could recapitulate the initial part, though the research
Yeah,
part is not purely my area.
yeah.
But actually, I was totally out of touch with antenna and other things for last 3 years. Thank you very much, sir, for
Okay.
recapitulating me with basics and those things. And
Thank you
we
very,
have
very much,
basically
Dr. Shaniwar.
mainly CS and IT students, sir. So ECE students might have benefited a lot.
Yeah. Yes, yes.
And
But
whatever who are
but
in background also, sir, they will also benefit, sir.
yes. Mm.
So thank you, sir.
Okay, thank you, Dr. Swanivar, for giving me opportunity to share some of my experience with the faculty members and the students, uh, and my best wishes for your the ongoing FDP
Thank you, sir.
from my side,
Thank you,
and
sir.
to have a wonderful and successful to you as well as to the benefit to the participant. Thank you very much.
Thank you, sir.
Mm. So can